Welcome everyone to the AI Fun with Ellis seminar. Today we have the distinct pleasure of having Jack from the University of Oxford, who's going to talk to us about joint work with his advisor Sam Staton. Welcome. The title is Compositional and Imprecise Probability, and the floor is yours. Thank you.
Great. Thanks everyone. Thank you for coming to my talk. I'm Jack. This is work I've done with my supervisor, Sam. I guess I'll launch into it. So just before I start, we do have a preprint paper out. So we just updated this one. So if you have any additional questions after I'm gone, then feel free to have a look at that. And we originally got accepted to POPL, so that will also come out with that conference. I guess the context of what we'll be talking about today. So basically we're going to be looking at probabilistic programming languages. So probabilistic programming languages is basically a programming language where we're trying to essentially encode statistical models. So that means basically commands in our programming language. We should have commands for basically sampling from basically distributions that we set up or that we are interested in, and then conditioning based on these samples. So here's a little example of a probabilistic programming language that some of the people in my group work on. And so basically what it's doing is it's performing a linear regression on a set of data points. So you basically have, I can see what's happening here. So basically sigma is just the noise from a data set. We have basically a set of data points from this set, and then we have some prior distribution. And this is a prior over a set of functions. And then the code here basically samples from the prior conditions based on these samplings and a score we have based on this linear regression, and then it returns our new posterior based on this conditioning. And we can perform an iterative loop over that, and then basically we'll perform a linear regression over these sample points here. And why this is useful is because when you're actually encoding your statistical model, you're basically, when you're programming your statistical model, or even just writing your statistical model, because the fact that this is actually encoding it into a language, you can very easily perform inference on it just by, say, like a Monte Carlo inference, just because, you've already got the model in your language there, and basically your model and the code for performing inference on it are like one and the same. An overview of what we're doing or how we're trying to push this type of idea further. So within this work, is what we want to do is give a fully compositional probabilistic programming language, which basically supports Bernoulli uncertainty and Knightian uncertainty. So Bernoulli uncertainty here is basically, you can think of that as tossing a fair coin. So very simple, basically probabilistic sample of, it's a command where we can think of that as we throw a coin, and there's a chance that it'll land on heads and a chance that it'll land on tails. And then we can use that outcome to continue within basically, within the term in our language. So in our case, we'll be basically looking at a fair 50-50 coin toss, and that's the only kind of probabilistic uncertainty we'll be having here. Now, we also want to consider Knightian uncertainty. So this is basically imprecise probability, where not only do we, so in regular uncertainty, say Bernoulli uncertainty, not only do we not know what the outcome will be when we toss a coin, but we don't know what the outcome will be, but we know what the distributions this outcome will be when we toss, say, a fair coin. In Knightian uncertainty, we're basically saying not only do we not know what the outcome will be, but we don't even know what distribution it will follow. So the only way we can really, I guess, encode this is basically as the set of all outcomes without any prior on what these outcomes might be. And so these things have been hard to combine for mathematical reasons, but we're trying to give an account of this basically using a graded perspective and naming the Knightian choices, which I'll go into later. And so we show two things about the work that we have. Basically, this gives a refined bound on the Knightian uncertainty, so the imprecise uncertainty that we have when we compose programs within this model. And also, it's the best we can do. We can't quotient this model any further without basically something breaking that we want to preserve. So there has been other work around other broader interests around basically combining non-determinism, which is basically Knightian choice and probability, so like Bernoulli choice. So yeah, there's a list of things here, some of which Sam has also worked on. But we are focusing purely in the setting of imprecise probability. So there's other reasons why you might want to combine these two kind of uncertainties with each other, but basically, there's different things that they want from basically these combinations, and we want a fully compositional account of imprecise probability, which has not been done before. All right. So first of all, what is imprecise probability? So we can think of basically a probability over a set of, say, 3 points, so red, green, and blue, as basically a point in the simplex or the triangle between these points. So we can think of basically the point at the tip of red as being the probability or the chance or the probability outcome of 100% chance of red happening and 0% chance of anything else happening. On the other hand, a probability, so the point P, say, in this top left triangle here, represents the chance of 50% chance of green happening and 50% chance of blue happening, but impossibility of red happening. And then the point directly in the middle, Q, basically represents equal odds chance of all 3 of these outcomes happening. And so you can extrapolate this and I guess get a one-to-one correspondence between every possible, I guess, probabilistic outcome and every point in the simplex between the outcomes. So if we think of basically, if we take the Bayesian interpretation of probability, these points would basically be the fair bet you would make given your probabilistic view of the world. So yeah, you would say, okay, if it's red, green, and blue, equal odds, the fair bet would be I'd put equal money on red, green, and blue. On the other hand, imprecise probability kind of generalizes this, and it says, okay, we don't have a purely probabilistic view of the world anymore. There are some inputs where we just don't even have access to what the prior or what the distributions of kind of these inputs to our world model might be. And in this case, we basically get sets of possible outcomes. And in particular, we get convex sets of distributions. And that's because if you think of it as basically the betting interpretation, if you're willing to put a bet on red and you're willing to put, so this is the top right triangle here, if you're willing to put a bet on 100% certainty of red happening, and you're willing to put a bet of 100% certainty of green and blue happening with equal odds, then you should be willing to put a bet of any convex combination of these, because this is basically a convex combination of your beliefs. And so you're kind of coherent with respect to your beliefs. So imprecise probability has been studied extensively, and there's been a huge range of applications of where this has been applied. So Wally, who's written a big famous book on it, in statistical robustness. It's got applications in economics, in engineering. Usually the imprecise probability comes in where basically you have maybe some models that you have some models of some systems, but then you're basically saying, okay, but you have a set of models of what the system might follow, but you don't know which model is the exact one. And say you want to adhere to some certain bounds or some certain safety measures, regardless of what your model might be. And then you would use an imprecise probability here, because regular, say just putting a normal distribution over these, over all your basically models doesn't quite cut it, because the expectation kind of just, balances over all of them. But really you want to make sure that regardless of the system, some kind of threshold is adhered to. And in particular, what I guess prompted us to look at this was its applications in machine learning. It's been applied in Bayesian learning by Michele right here in the room, but then also in reinforcement learning, in conformal prediction, and then recently in the foundations of safe AI. So this last part is what kind of got us onto it, where the ARIA, I guess, a new ARIA team is looking into trying to create safe AI with these types of ideas. Okay, so looking at our actual first language. So basically what we want in our language, so this is a programming language. We're going to keep it very simple, basically to highlight what the impacts of our of combining both our Bernoulli choice and our Knightian choice are. So in this language, what we will have is basically if then else statements. So we condition on a Boolean B, and if it's true, we continue with T, otherwise we continue with U. This kind of gives us our conditioning on probabilistic choices. We'll have let bindings. So basically, we run term T, and then whatever the result of that is, we'll bind to X, and then we can use X in U. So whatever X, the result of T is, will be bound to X, and when we call T X in U, it will be that same result. And finally, we're gonna, also have two commands for basically implementing our probabilistic and non-deterministic choice. So Bernoulli, our command Bernoulli is basically just, you can think of it as flipping a coin with equal chance heads and tails, or you can think of it as equal chance true and false. And so, there's a 50% chance that this command will return true and 50% chance this command will return false. Our Knightian command, on the other hand, you can think of it as basically someone giving you a coin, saying it's biased anywhere between 0 and 1. So maybe it's a coin which always returns true. Maybe it's a coin which always returns false, but you don't know, it's biased somewhere between there. Then you flip that coin, and whatever the result is, true or false, you continue with that one. So we have no prior on what the distribution of the Knightian choices are. And we're not interested in flipping this coin and trying to figure out what this distribution is. Basically, you get the coin, you flip it once, and that's it. You continue with that Boolean. You can't reflip these coins. So how can we actually encode these basically imprecise probabilities or convex sets with programming constructs like these? We can think of basically on the top left triangle here, we can read this program as basically we flip a Bernoulli coin, we bind it to Z, and then we condition on the result of this Bernoulli coin and return green if it's true and blue if it's false. So in this case, we basically have 50% chance of green happening because it's just a Bernoulli coin. So we know it's 50% chance true or false, and 50% chance blue happening. And so we get this singleton point here, 50% of the way between green and blue. Now we can increase this complexity by a little bit by basically flipping, in addition to a Bernoulli coin, a Knightian coin. And so this is where we start getting these sets of outcomes because we now have no priors on the distributions of the Knightian coins. So here we flip a coin Knightian, bind it to X, flip a coin Bernoulli, bind it to Z, and then use some programming logic in order to combine them together. And the way you can interpret this program is basically we can look at the two extreme cases of what the coin is, of what the Knightian coin is when it flips. In the case when it's 100% chance of being true, basically what will happen here in the first branch of the if statement, this will return red because X is 100% chance of being true. And in the second branch, X will also return red because it's 100% chance of being true. And so in this whole program combined, no matter what Z is, we'll get the outcome red. And so we can see that's represented by the point at the very tip of red there. On the other hand, if X was, say, the coin that came from, if the Knightian coin that was flipped was 100% chance of being false, then we follow through with the same logic, and we can see that on the first branch, we'll always return green because it's always false, X is always false. And in the second branch, we'll always return blue because X is always false. And so we can see that this is the 50% chance between green and blue there. And then we can think of all possible distributions of the coin. It's basically all possible convex combinations of these two outcomes. And so we get this convex set between 100% chance red and then 50% chance green and blue. So we can actually identify these convex sets just with their extreme points. And that's how you mostly reason about these types of programs. So in this final program here, we're just going to increase complexity a little bit more. Where we run the same program, except on the second branch, instead of conditioning on X again, we condition on a new Knightian coin toss, Y. And so now we can look at the four possible outcomes, or the four possible extremal outcomes, which is X being 100% chance true and Y being 100% chance true, X 100% chance false, Y 100% chance false, and then false and true, and then false and false. So in X being 100% chance true and Y being 100% chance true, we again get this tip of the triangle here. 100% chance red. False and false, we again get this tip here, green and blue. But now that there's no, I guess, dependence of X and Y on each other because we've pulled them from different Knightian coins, we have the chance where X is 100% chance true and Y is 100% chance false, so this gives us 50% chance red, 50% chance blue, and on the other way, we get 50% chance red, 50% chance green. And so those are the four possible extremal outcomes. We can take the convex combination of these, and we get this diamond-like convex result here. All right, so that's what the program's going to look like. I hope I didn't, okay. So that's what we want the program to look like. What kind of, I guess, desirabilities do we actually want from our programming language? What will we like it to actually adhere to? So yeah, the first one is that our programming language should be commutative. So basically, what this means is if we have some program T, which returns a value, which we bind to X, and then some, I guess, term U, which returns a value, which we bind to Y, and then we continue with V. If X is not free in U, so if U doesn't mention X at all, and Y doesn't mention, and T doesn't mention Y at all, so basically these two let bindings are independent, then we should be able to switch them around. And you can think of that as basically in probabilistic terms, if we throw one coin, wait for the result, throw another coin, wait for the result, and then finally we do something with the outcome of these two coins. It wouldn't have mattered whether we threw this coin first and this coin, or this coin first and this coin. They should be the same thing. So this kind of represents, I guess, Houdini's principle here, where you can rearrange, you can rearrange conditions which don't depend on each other. And then we also want affinity. So this means basically if we, perform some probabilistic, if we run some term and bind the output to X, and then we continue with U, but U never mentions X in the first place, then it should be the same as just running U without having performed this term T and binding it to X. So we can think of it as we flip a coin and then we never look at it again, and our model has no reference to it, then it doesn't matter, we didn't need to flip the coin in the first place. So what this allows is us to actually additionally represent our programs as these data flow diagrams, because there's no ambiguity as to whether we perform term T and then U, and then continue with V, or whether we performed program U and then T, and then continue with V, because we can represent these this way as they'll be equal. It doesn't matter which way we interpret these as which one we interpret as happening first. Okay, and for our second piece of desiderata is basically we want standard equational reasoning about if statements. And the one we're going to be looking at in particular is this one here. So basically, if we perform some conditional on some Boolean B, and then in each of the branches, we run the same term T, bind the result to X, and continue with another term, then that should be the same as basically just hoisting this let binding out and running the term, binding it to X, and then running the if statement, provided, of course, X is not free in B. So it shouldn't matter whether we run this let binding before or after, as long as the let binding within each of the branches is the same. Because in the end, one of the branches will execute. One of the branches will execute, so it doesn't matter if this happens before or after. It will never be executed. Cool. Okay. All right. So before we jump into, I guess, how we actually, the problem and the solution, the way we often implement these types of, I guess, additional structure to programs, so here basically randomness and uncertainty and imprecise probability, is we do this using monads. So monads, I'll give a brief introduction. Unfortunately, they're rather abstract concepts, but I'll give the definition here, and then I have an example on the next slide, which will hopefully make it a bit more concrete. But yeah, because they're so abstract, which makes them also very powerful. So basically, what is a monad? It's basically a mathematical abstraction that captures sort of computational effects in programming languages. So computational effects is anything which isn't basically a program which is run purely like on a computer. Basically, you can think of a pure programming language as one which is basically like a mathematical statement. But computers obviously have a lot more power than that. They can read and write to memory, they can invoke randomness, they can ask for user input. And so functions which actually invoke those types of effects, we call them effectful, and we call the effects computational effects. and then we represent these. Yeah, so Mudgee in his seminal papers showed that we can actually represent a whole range of these using this construction of a monad. So the way they work is basically, we can think of a program which takes in maybe some input x and returns a y. So maybe you can think of it as a function which takes in an integer and returns a boolean and tests whether it's even. Rather than just returning a pure value y, we actually return a value in a computational context, which we call ty. T here is what we call the monad. So you can think of, yeah, well, I'll give an example on the next slide. So yeah, instead of looking at programs x to y, we look at programs x to ty. And you can think of T as maybe some data constructor, like a list or a set, or you know, a maybe monad for those who've done a bit of functional programming. But we also need some additional structure on this monad, because now, well, immediately we break composition. Because if we have a program from x to y and a program from y to z, but now they're interpreted as a program from x to ty and a program from y to tz, they no longer can be combined together because there's a tight mismatch. So we need this structure, this second one here, where if given an x to ty and a y to tz, we get an x to tz. So we need a way to actually compose these things. Also, we can think of maybe functions which inherently are pure. So say a function, yeah, which tests if it's an even, like maybe we are in an effectful language with state and stuff, but testing if even doesn't need that state. We need a way to be able to lift this program up into our new framework so that we can actually interpret it there. So we need a way to interpret a pure function basically in a computational context where the context means I'm not actually doing any computations, but it is in this framework. And then we have some other combinations here. This last part isn't necessarily a monad. It's a bit stronger than a monad, but we often need this in programming languages. So sorry, that was quite abstract, but I'll try and, I guess, make that a little more concrete with an example. So non-determinism we can think of non-determinism as an effect where basically you're running a program and maybe you come across a choice where it's like, you know, one choice is go down this branch and one choice is go down this branch. But basically, and basically, so it's basically, you can think of maybe like a random decision, or you can think of it as doing everything. So we want all possible outcomes. And so, yeah, the way we would model this type of effect is basically with a power set. So instead of taking a single item, we take a set of results. So now when we have a program x to y, and so we would usually consider that as given an x, it will return a y. What we can instead do is say, okay, given an x, I can return multiple y's. So given an x, instead of just returning a single y, I can return a subset of whatever the y's are. Okay, and now we also need to interpret this additional structure. So these pure programs, x to y, we can still interpret as pure programs. All we do is say, okay, if you give me an x and I give you a y, well, instead of giving you multiple y's, I can just give you that y, but as a singleton set. So even though it is in this computational context of being a subset of y, it's basically the do-nothing computational context. I never returned multiple values. I still returned the only value you had, but now in this new framework. And then when we want to compose, so say we have an x1 to y1, y2, and the y1 and y2, so and y is a function where y1 gets mapped to z1, z2, and y2 gets mapped to z2, z3. Well, in order to compose these things, what we would do is we would first run the function x1 and get a y1 and y2. Then for each outcome, we run this function again. So we run our new function. So we run it on y1 and we get z1, z2. And we run it on y2 and we get z2, z3. And then we take the union of all possible results. We say every possible outcome of running these branching programs is what our composition will be. And so in the end, we get a mapping from x1 to z1, z2, and z3. And then here, when we want to take, I guess, and here when we want to compose these functions basically side by side instead of one after the other, we basically take the outcomes of the two functions and then we take the product of them. So we have a function x to y1 and x dash to y1 dash. This will, when we compose them monoidally is what we call it. So side by side, we get a program from x and x dash to y1 y dash y1 y1 y2 dash. Yeah.
Don't you know, has monad approach ever been used for conformal prediction? Because it looks, the first line especially, it looks a lot like what the conformal prediction does. That is, give me a new input X, and I will output a collection of labels that make sense for that input. And also, especially, and in the structure, okay, the second one is not necessarily useful for us. It will satisfy it, but trivially. The third one is kind of interesting. So I think there's potential there to maybe, because of the power of this approach, of the abstraction of this approach, maybe something could be unfolded there. Do you know if somebody has done it?
I wouldn't be surprised. I'm not too familiar with your effects for conformal prediction, but non-determinism has been used to do like a lot of things. It like, even though we're interpreting it in the Knightian choice, the people could interpret it for all sorts of other things. So especially like program refinement, where maybe you have one program, or you're trying to find maybe a set of outcomes which satisfy it, and then you cut down the program based on more and more restrictions you put on what the outcomes can be. That's also done with non-determinism. But yeah, no, we can chat about it later. That sounds interesting. All right, so hopefully that was a very brief but insightful introduction into monads. So what is the actual problem we come across when we're trying to combine this Bernoulli uncertainty, which is modeled by a monad called the distributions monad, and Knightian uncertainty, which is modeled by this non-determinism monad, because it is just all possible choices. Well, there is one monad which captures both of these two things. It's called the convex power set, or convex power set of distributions. And that monad basically that monad, rather than returning a set of outcomes of Y, say, it returns a set of distributions on Y, and that set has to be convex. So we can interpret the commands Bernoulli and Knight in our language within this monad. So Bernoulli basically returns a singleton set of 50% chance true and 50% chance false. So that is a set of distributions. And the Knightian command returns the convex set between 100% chance true and 100% chance false. So this monad can actually interpret basically the programming language constructs we're after. However, we find that if we have this, say, function in our program here, which is similar to the one we saw earlier, if we actually toss the Knightian coin and then the Bernoulli coin and interpret that in our language, basically we'll get the convex set on the right here. Sorry, if we toss the Knightian, Bernoulli, and then run this logic, then we'll actually get the convex set on the left here. However, if we toss the Bernoulli coin and then the Knightian coin and then run this program logic, we'll actually get the convex set on the right here. So this monad is actually not commutative, so it doesn't respect basically this reordering of the coin tosses, and so it doesn't actually satisfy what we want from our language. And it turns out, if you have just any semantic model, so any mathematical model which satisfies all the desiderata that we have, we can actually prove that it can't distinguish these two convex sets. So if we have something which satisfies the conditions we want, we know it will never be able to respect imprecise probability, because it won't be able to tell these two different imprecise probabilities apart. And the reason is basically this kind of function here. So when we toss so we can think of it as tossing a Bernoulli coin, conditioning on it, and then within each of the branches, we toss a Knightian coin and condition on that. And the paradox kind of arises in the program on the left. Because the Knightian coins are bound to the same variable, we can think of them as the same Knightian choice, so they're not so they're dependent on each other. And then we'll either return 100% chance red or 100% chance green and blue and the convex combination, but we'll never be able to return either red and blue or red and green. But we can also interpret this program as basically each of the Knightian coins happening from a different, each of the Knightian tosses happening from a different coin, and that will give us the convex set on the right here. And basically, yeah, without desiderata, basically any interpretation cannot distinguish between these two cases. Yeah, you can show that they are equivalent. So how did we plan to solve this? Well, okay, so our solution is basically to label the Knightian choices. So what we do instead of just calling a regular Knightian command, we have a label which goes into the Knightian command. So we can see that on this, on the program at the top here, so even though we still have X and X, we actually have a label which we plug into the Knightian command, A1 and A1. And that tells us whether these Knightian coin tosses are basically dependent on each other or independent. So in this first one, we basically have, we condition on the Bernoulli coin toss. And then in the first branch, we condition on a Knightian coin toss. And the second branch, we condition on the same Knightian coin toss. And so that indeed gives us the convex set of the single line earlier, because there's only one Knightian coin toss which is going on. And so, we'll either get basically the two extremal points are 100% chance red or 50% chance green and blue. And we can't, there's no way to get red or green or red or blue because, there's no way to get these probability distributions disjoint from each other because they came from the same coin. On the other hand, now if we label them with different coins, so now we toss X from a Knightian coin A1 in the first branch and X from a Knightian coin A2 in the second branch, now we're explicitly saying, okay, these two coins are independent of one another. And so, it can indeed be the case where the first coin is 100% chance heads and the second coin is 100% chance tails. And in that case, we can indeed get this 50% chance red and 50% chance blue outcome. All right, so how do we actually use this idea and build a monad out of it? So that we can actually encode it into our programming language. So what we do is we take the reader monad. So the reader monad is basically given, the reader monad you can think of as a function from a specified set, in our case 2 to the a, into the output, so X. And so you can think of that as you can read from the sets A, and it will give you, so if you plug in an element of the set 2 to the a, it will give you an element of the output set. And this is a reader monad transformer over the finite distributions monad. So the finite distributions monad is basically the monad which gives you all possible finite distributions of X. So you can think of those as just regular probabilities or just a point in the simplex. Now we can encode Bernoulli choices by basically these finite distributions. So that's this dx here. So we can think of this as, the 50% chance heads, 50% chance tails result. We could encode as basically a distribution. If X was the outcome of a coin, heads or tails, we can encode that as a distribution of X as 50% chance true and 50% chance false. But we additionally have this reading ability. And this is how we encode the Knightian choices into our monad. So you can think of the set 2 to the a as basically being A is the set of Knightian choices. This is the names of all the coins that we are able to toss. And then 2 to the a means, okay, for each A we have 2 possible outcomes. And this we will interpret as basically the outcome being 100% chance true and the outcome being 100% chance false. So we're kind of considering our imprecise probabilities only by their maximal output, by their maximal points. But because these things are one and the same, we can represent an imprecise probability by its maximal points. These things are equivalent. We can basically, so we have 2 to the a types of possible. So given a 19 coins, we have 2 to the a possible extremal outcomes. And so this function here, you can think of as giving one possible outcome of all the 19 coins. So say A is 3, if 2 to the a will be 8. So you can think of this as heads, you can think of this as all possible combinations of 3 coins of heads or tails. And so you can plug maybe heads, tails, heads in, which represents, the non-deterministic path or the 19 path where one coin was 100% chance heads, one was 100% chance tails, and one was 100% chance heads. And that will give you the distribution. That will say this is the distribution if these following extremal points happen. And then, so for each of these extreme, and this will give you 2 to the a possible extremal outcomes. And then the way we can recover, before we do that, instead of looking at this 2 to the a, so instead of looking at this as basically sets of coins, and then we put to the power of 2 because those are the possible, those are the sets of possible outcomes. we generalize this to a set B. So basically you can think of the set B here as being, okay, these are the possible non-deterministic paths we can take. And if we plug in a B, so say the size of B is 5, we'll say there's 5 possible non-deterministic paths. And for each B we plug in, we get a different distribution. And then basically the convex hull of that distribution will be our imprecise probability, because we're saying we have 5 extreme points that we can take, and then the convex hull is all possible combinations of these extreme points. And then from this monad, we can actually indeed recover the convex power set monad, basically by looking at all possible distributions on B. So this is what I was saying earlier, where we look at, well, equivalent to what I was saying earlier, where we look at all possible distributions on B. So we can think of B maybe as its own probability, and we look at every single possible, I guess, convex combination of B, and then we push that forward on the function here to dx to find out what all possible distributions on X are given the paths given the non-deterministic paths we have access to. So you can think of this as basically, plugging in for each for all possible values in B. We plug in each value of B, we get a distribution, we take the convex hull of that distribution, and that is indeed a convex set of distributions, and this is the equivalent convex power set that we'll get in the end. So we can recover the original convex power set that we use to interpret the imprecise probabilities. Okay, so sorry, this is going to be like the one slide of super technical details just to get all the definitions out there. So the issue with, so the problem with just these names is, okay, we do have, say we have a program with one set of names and a program with another set of names. Well, we need to figure out how we can actually compose these two together. So what should we actually do on conflicting sets of names? And how can we actually talk about these compositions of programs? Because, we now have kind of additional argument A within our monad. And the way we interpret this is basically with a graded monad structure. And what that means is basically, so a graded monad structure is basically a generalization of a monad where you can kind of tag your monad with additional information. And this additional information gets propagated through following some looser monad laws. So we can think of this monad structure basically. So if we think, the way we interpret our programs in this structure is, okay, so we have the monad T, and then the subscript is basically kind of the size of the non-deterministic paths, and then the X is basically the size of our outputs. So we can interpret Bernoulli in this monad, or this graded monad, as the monad with grade 1, so we only have one non-deterministic path. When we toss a Bernoulli coin, it's 50% chance heads, 50% chance tails. There's no non-determinism which is happening. We're fully confident we have no impreciseness within that coin toss. So there's one non-deterministic path and two possible outcomes. The first is 50% chance true, the second is 50% chance false. And so we can represent this as basically a matrix with columns of size columns of size A and rows of size X, because we can think of each of the possible columns is a probability vector, and each of the possible columns is a non-deterministic output, and the output is given by the probability vector of the column. And 19, on the other hand, okay, when we toss a 19 coin, there's two possible non-deterministic paths it can take, heads or tails. And so we interpret this as basically in the monad a grade 2, and with output 2, and basically we look at the two extreme points, 100% chance heads of happening or 100% chance tails of happening, or true and false, however you want to interpret it. So we can indeed interpret our commands within this monad. And then when we look at functional and monoidal composition, so here we have these same compositions as before. When we have a function from X to A, T A Y, and Y to T B Z, so we can think of this as one program which invokes A non-deterministic choices and returns X, and another program which takes and returns Y, another program which takes a Y, invokes B non-deterministic choices and returns a Z. Well, when we compose them together, we get a set of a grade of type A times B. So we look at all possible non-deterministic paths in the first branch, combined or independently combined with all possible non-deterministic paths in the second branch. And so we these grades add on to each other so that we were able to, look at programs with bigger and bigger non-deterministic choices in them, so that we can, indeed compose these programs together. And we do this similarly with the side-by-side or monoidal composition, where if we have two functions that we put side by side, we look at the output, which is basically all possible outputs where we look at, the outputs where we look at all possible non-deterministic paths in the first case, in the first function, with all possible non-deterministic paths in the second case. So we take the total set. Okay, so what results have we actually shown about our construction? So first of all, basically, as alluded to earlier, there is a mapping which basically takes an element of our monad or TAX into the convex power set monad. And that's represented by this picture at the top here. So we can think of this as basically, there's two probability vectors. And if we think of the three outcomes as red, green, and blue, in the first one, we have 100% chance of red. Second one, we have equal chances between green and blue. So we basically map each of these probability vectors into the simplex and take the convex hull, and that's how we recover our mapping to the convex power sets. So what we've actually shown is this mapping induces a Oplax functor, is what it's called. But basically, what it does is it means we show that there is a mapping from programs in our language to programs in the language with convex power sets. But our language is, of course, fully compositional. The convex power sets is the one which isn't. But we can recover these convex power sets, so we can recover programs in the sense of imprecise probability. And we've also shown that given this mapping, this Oplax functor, so not only is there a mapping, the Oplaxness, what the Oplaxness means is that we actually have tighter bounds on the imprecision in our program when we compose programs together than if we were to compose programs, if we were to map them across and compose programs in the new setting. So you can think of, say, programs G and F as being in our language. If we compose them together in our language and then map them across, we actually have tighter bounds on the imprecision. So the convex sets are actually smaller, or at least as small as the convex sets we would get if we were to map each function individually and then compose them in the convex power set framework. And the reason for that is because we've actually named the 19 choices, we can actually talk about when on different branches, the set of different choices actually come from the same coin, which is something you can't do in the convex power set monad because you kind of forget the name information when you make this mapping.
So this is for a more statistical audience, this would be like sharing information, like
So you can actually share information between.
That's why you get narrower bounds.
Yeah, basically, and that's why we get the narrow bounds. So we can share information, share the what the coin toss was, and of course the bounds are narrower. In the convex power set, you actually forget about these, and there's no way to recover which of these were actually. You forget about the names, and there's no way to recover which programs shared which 19 tosses with what. And so the best you can do is assume that everything is completely independent, and so you get this this subset relation here. And the second part of our theorem is basically, the second result we have showed is, so this mapping is actually from basically our framework, so programs in our language to programs in the convex power set language is not injective. So there's actually more programs in our language which will get mapped to the same program in the convex power set language. And you can think of this like an intuitive reason is we interpreted 19 as 100% chance true. The first non-deterministic choice as being 100% chance true, and the second non-deterministic choice as being 100% chance false. But if you swap them around, that's a different program because the actual matrix are different. But of course, the convex hull, when you map them to each respective thing, you still get 100% chance false, 100% chance true. And then you take the convex hull, that will be the same convex set. But of course, these are, the original things are different. And so this actually is a non-injective mapping. So the question is, can we quotient our framework any further? Can we identify things so that we have, so that we can make this mapping potentially non-injective, so that we can have a one-to-one correspondence between our language and actually like convex or imprecise probabilities. And we showed that we answered this question negatively, so we cannot. And basically the reason is, if we try to equate any two more programs in our language that are not already equated by their interpretation in the monadic language, basically what will happen is either we will break the connection with convex subsets, so we'll equate two programs which represent two different convex subsets, which of course breaks the connection with imprecise probability. So yeah, we won't have this correspondence between our language and imprecise probability. Or if we don't break that, we'll basically break the compositional structure. So it will no longer be the case that we can compose programs willy-nilly and do this reordering of independent terms and affineness without basically changing the program. So I guess in conclusion, in this work, basically we use a graded perspective and named 19 choices in order to give a fully compositional account of Bernoulli and Knightian uncertainty together in a probabilistic programming language. We showed what this gives us is actually a refined bound on the uncertainties, on the Knightian uncertainty, so smaller convex subsets. And also it's a maximal approach. So there's no other way we can quotient down without basically breaking something. And yeah, so for future work, what we plan to look into is adding iteration to our language, so some kind of recursion and infinite dimensional convex structures. So at the moment, we can only support have finitely generated convex subsets, but yeah, we want to be able to, of course, make this infinitely generated just to maximize the generality. But things unfortunately break when you try and add infinite Knightian choices, at least with what we have right now. Also being able to incorporate function spaces, so be able to have higher order languages where functions themselves can take in functions and use those functions within their methods. And yeah, so that obviously generalizes, that's a very powerful thing in functional programming. And there's research in quasi-Borel spaces, which looks similar to well, it's how you basically do that in probability monads. So yeah, that's another future direction. And then of course, looking at implementations or statistical inference using these programs and approximation of bounds and trying to perform some kind of statistical inference with these things is another question, because sampling in imprecise probabilities is a non-trivial question. So yeah, okay, references. That's me done.